Welcome to this module on survey tools and technology. Accurate wellbore surveys are the backbone of directional drilling, as without reliable data on inclination and azimuth, we cannot confirm the well's location, nor ensure it avoids collisions and hits the reservoir target. Over the decades, survey technology has evolved significantly, from basic inclination-only tools that simply confirmed verticality to modern measurement while drilling, MWD, and gyroscopic systems that deliver real-time, high-precision data. Each technology has its own applications, limitations, and accuracy levels, and choosing the right tool depends on well objectives, formation conditions, and cost considerations. In this session, we'll explore the range of surveying tools, understand sources of magnetic errors, and discuss how to mitigate them using non-magnetic drill collars. We'll also compare the strengths and weaknesses of each survey system, from Totco discs to modern MEMS-based gyros. The module has been divided into 3 submodules. This is the first submodule of 3. At the end of this module, you should have 4 clear takeaways. First, you'll be able to list the various types of surveying tools used in directional drilling. Second, you'll understand the sources of magnetic survey errors, including drill string interference, crustal field variations, and magnetic variance. Third, you'll be able to calculate non-magnetic component requirements for a BHA, ensuring survey instruments are isolated from magnetic interference. Finally, you'll be able to briefly describe the commonly used surveying tools, state when each is most effective, and explain their similarities and differences. These objectives matter because survey data underpins all directional drilling decisions. A well steered with bad survey data risks missing the target or colliding with another well. By understanding both the tools and the error sources, you'll be able to critically evaluate survey data and ensure it is fit for purpose. Keep these 4 objectives in mind as we move through the details. They will frame our discussion and give you practical knowledge for real-world applications. Survey tools fall into 2 broad categories: inclination only and inclination plus azimuth. Inclination-only tools are simple, inexpensive, and mainly used to confirm verticality. Classic examples include the Totco tool, which used a spring-loaded plunger to punch a hole in a waxed disc after drilling, and the andadrift or teledrift mechanical devices that transmitted inclination via pressure pulses while drilling. While basic, these tools still have niche applications where low-cost monitoring is sufficient. More advanced systems provide both inclination and azimuth. These include magnetic azimuth tools like single-shot and multi-shot cameras, steering tools, MWD, LWD systems, and gyro tools that provide azimuth unaffected by magnetics. Gyros themselves come in several types: free gyros, rate gyros, north-seeking gyros, and inertial navigation systems, increasingly incorporating MEMS technology. The evolution from simple mechanical to digital real-time tools reflects the industry's demand for higher precision and efficiency. Today, the choice of tool depends on well complexity and accuracy requirements. Vertical wells may still use inclination-only checks, but modern deviated and horizontal wells demand continuous high-fidelity surveys from MWD or gyro systems. Magnetic surveying relies on Earth's magnetic field, but that field is dynamic and imperfect. The dynamo theory proposes a mechanism by which a celestial body, such as Earth or a star, generates a magnetic field. The dynamo theory describes the process through which a rotating, convecting, and electrically conducting fluid can maintain a magnetic field over astronomical timescales. A dynamo is thought to be the source of the Earth's magnetic field, as well as the magnetic fields of other planets. To fully define the Earth's magnetic field at any location, we need 3 components of a vector. The field strength, usually measured in nanoteslas or microteslas, the declination angle, defined as the true direction of magnetic north, and the dip angle, defined as the vertical dip of the Earth vector below horizontal. For computing reasons, this vector is often defined as 3 orthogonal magnetic field components pointing towards true north, east, and vertical. Surveying accuracy depends on accurately accounting for these variables. However, the field itself fluctuates due to solar activity, crustal anomalies, and the long-term drift of the magnetic poles. For drillers, this means magnetic surveys can never be perfectly stable. Organizations like the ISCWSA provide standardized models to predict and correct for these variations. Still, residual errors persist, and they increase with depth and proximity to magnetic interference sources. Understanding the fundamental limitations of Earth's magnetic field is the first step in recognizing why survey errors occur, why non-magnetic collars are needed, and why gyros are often required when magnetics cannot be trusted. Magnetic survey errors generally arise from three sources: drill string interference, magnetic variance, and crustal field anomalies. Of these, drill string interference is the primary factor, accounting for more than 85% of errors. Interference occurs because magnetic survey tools sit inside steel BHAs. Ferric steel components generate their own magnetic fields, which bias the readings of the tool. We categorize this interference as coaxial, aligned with the tool axis, or cross-axial, acting perpendicular. Errors vary depending on well trajectory. When drilling east-west, the z-axis picks up more interference because it is perpendicular to Earth's field lines, leading to significant azimuth errors. By contrast, when drilling vertically, interference is minimized because the tool is aligned with Earth's field. Magnetic variance, on the other hand, reflects temporal changes in Earth's magnetic field, while crustal anomalies are localized distortions caused by iron-rich formations. Recognizing these sources allows us to design BHAs with sufficient non-magnetic spacing and apply corrections. Ultimately, knowing where errors originate empowers drillers to select the right survey tool and interpret results with confidence. About 85% of all magnetic survey errors come from drill string interference, magnetic variance or magnetic disturbance field, and crustal fields. Generally, the remaining 15% comes from other errors, such as systematic, tool accuracy and/or calibration errors, or human errors, workmanship errors. Drill string interference refers to the additional magnetic field resulting from magnetic material placed close to the magnetometers of the MWD tool. Magnetic variance refers to all the possible changes in the total magnetic field at the drill site, depending on a number of factors: solar storms, time-based changes of the Earth's magnetic field, etc. The magnetic declination in a given area may change slowly over time, possibly by as little as 2 to 2.5 degrees every 100 years or so, depending on its distance from the magnetic poles. For a location closer to the pole, the declination may change by 1 degree every 3 years. This may be insignificant to most travellers, but it can be important if using magnetic bearings from old charts or meets, directions, in old deeds, for locating places with any precision. Magnetic variance due to solar activity cannot be corrected for, so it is essential to monitor and be aware of its effects during solar storms. Crustal field. This is the additional magnetic field resulting from the localized effects of magnetic rock in the basement formations of the drilling site. This can be a significant source of error in MWD. The global models, such as the BGGM and HDGM, can only take into account the longer wavelength variations in the Earth's field and cannot be expected to allow for the localized effects of magnetic rock in the basement formations. In order to correct for these effects, the magnetic field has to be measured on site. Drill string interference is the single largest source of magnetic survey error, accounting for over 85% of inaccuracies. It comes in two forms: coaxial and cross-axial interference. Coaxial interference occurs when the steel components of the BHA create a magnetic field aligned with the tool's axis. This biases azimuth calculations and is especially pronounced when drilling east-west, because the z-axis sees a proportionally high contribution from drill string magnetism. Cross-axial interference, meanwhile, occurs when stray fields from collars, stabilizers, or motors affect the survey tool from the side. The effect depends on both inclination and azimuth. Vertical wells suffer less because the tool is aligned with Earth's field lines and perpendicular influences are minimized. But as inclination increases, interference grows, particularly in horizontal sections where tool orientation relative to Earth's field shifts continuously. The outcome is a significant azimuth error if not mitigated. Recognizing how interference manifests helps us understand why non-magnetic drill collars are essential. Without proper isolation, survey readings reflect a distorted local field rather than the true magnetic vector. By designing the BHA with the correct non-magnetic spacing, we reduce this effect and maintain confidence in survey accuracy. Magnetic components in the BHA act as bar magnets, with each end being a monopole. The field intensity created by this monopole is a function of the pole strength and its distance from the magnetometer. All assemblies will create an interfering field. Monell can reduce the effect and the algorithm can correct. Axial interference acts along the long axis of the BHA and is usually the much stronger component. Simple single-station corrections assume that all drill string interference is axial. Cross-axial interference acts at right angles to the long axis. It is difficult to correct and creates noise that can impact simple corrections, creating no-go zones for these algorithms. The azimuth error caused by axial magnetic interference is a complex function of hole direction, tool orientation, the local magnetic field vector, and the intensity of the interfering field. Often, in high-inclination east-west wells, even with considerable non-magnetic components to separate the sensors, there will be azimuth errors. The inclination is the multiplier, highly deviated versus straight. Whatever we do here does not affect external interference. Interference from casing, fish, etc. cannot be corrected for, and magnetic surveys that are affected by external interference should not be accepted as valid. The practical effect of drill string interference is a bias in azimuth calculations. Coaxial interference creates a constant offset, meaning every survey station carries the same angular error. Cross-axial interference is more variable and can cause inconsistent errors depending on the hole's azimuth and inclination. The impact is magnified in east-west wells, where the local magnetic field is weaker along the z-axis, making the survey tool more vulnerable to magnetic distortion from the BHA. In contrast, vertical wells are less affected because the tool is aligned parallel to the Earth's magnetic field. The deeper implication is that azimuth errors increase in critical sections, such as long horizontals, where anti-collision and reservoir navigation require the highest accuracy. Even a 1-degree azimuth error can translate into tens of meters of lateral displacement at depth, potentially missing a reservoir target. This is why drill string interference is carefully modeled using specialized software. Tools such as SLB's EDI calculator can estimate the expected error and determine how much non-magnetic spacing is required. The goal is to design a BHA that minimizes interference to keep predicted azimuth errors below acceptable limits, typically less than 0.25 degrees. Note, in this example, the z-axis is the coaxis. This is not the case for all direction drilling companies' tools. Let's take a look at the graphics on the right. The green triangles represent the Earth's magnetic field as vectors. The top left corner is magnetic north. The top right corner represents true north, and the bottom represents our current location in time. If we have insufficient non-magnetic material to isolate our MWD, a field strength generated by the string will interfere with our MWD measurement along the axis of the drill string. This is the z-axis for most companies. SLB, however, generally uses the x-axis along the string axis. When the drill string is drilling in a northerly direction, the interference created by the field strength of the BHA is added or subtracted to the adjacent side of the right-angled triangle along the north-south vector axis. As can be seen in the graphic, this has a negligible effect on the resultant angle theta. If, however, we are drilling in an east-west direction, we are going to add or subtract the field strength of the BHA interference to the much smaller east-west vector opposite side of the magnetic field triangle, meaning a proportionally much larger distortion to the azimuth. This can be seen in the angle in the right side triangle θ1. To combat interference, magnetic survey tools are housed in non-magnetic drill collars, NMDCS. These collars are made from non-ferrous alloys, often non-magnetic stainless steel, which provide the required strength while not distorting Earth's magnetic field. By isolating the survey instrument inside a sufficient length of non-magnetic drill collars, we shield it from the magnetic influence of the ferric drill string above and below. It's important to remember that in this context, magnetic refers broadly to any tool that relies on measuring Earth's magnetic field. MWD systems, steering tools, and multi-shots all fall into this category. If they are placed inside standard steel drill collars, the readings will be compromised. The required NMDC length depends on factors such as hole inclination, azimuth, and latitude. For example, wells drilled east-west and at high inclinations need longer non-magnetic spacers because errors are amplified in these geometries. The message is clear. Whenever magnetic tools are used, adequate non-magnetic collars must be included in the BHA design. Skipping this step is not just a technical oversight. It creates systematic survey errors that cannot be corrected afterwards. 7. Even with non-magnetic collars, drill string magnetization can still affect survey tools if not carefully managed. The required length of NMDCs depends on three main factors: the amount of steel above and below the survey tool, the well trajectory, and the geographic location. The closer the steel is to the tool, the stronger the magnetic distortion. Trajectory also matters. Errors increase with inclination, especially in east-west drilling, where the survey tool is perpendicular to Earth's main magnetic field. Finally, latitude influences the dip angle of magnetic field lines, which in turn affects the tool's sensitivity to interference. Compass error therefore grows, as well as deviates from north-south alignments, and increases as inclination increases. Operators must calculate the required NMDC length to ensure that residual interference is kept within tolerance. Failure to do so results in systematic azimuth bias. At the surface, this may seem small, fractions of a degree, but at reservoir depth, these translate into significant lateral errors. That's why BHA design isn't just about hydraulics or torque and drag. It's also about magnetic environment control to safeguard survey accuracy. As we conclude this sub-module, you should now be able to list the various types of surveying tools. You should also be able to identify the sources of magnetic survey errors, drill string interference, magnetic variance, and crustal field anomalies, and explain why drill string interference accounts for most of the inaccuracies. In the next sub-module, we will explore how to calculate non-magnetic component requirements for a directional BHA, ensuring survey tools are shielded from magnetic distortion by sufficient non-magnetic drill collars. Finally, we describe the commonly used survey tools, explain when each is most appropriate, and outline their similarities and differences. This completes this sub-module. Please move on to the quiz. Thank you.